So in this lecture we are going to continue electron beam lithography, but in particular we are going to look at the resist process. So far we discussed about how to profile the beam and what are all the important components in the lithography system and how complex the system is to have dynamic control of the beam. But once the beam is profiled and focused, and then it will be shot onto the wafer that has resist, right. So this resist is sensitive to electrons now. So optical resist, that is photoresist, are sensitive to photons, the energy, right, and then in this electron beam resist, so the resist is sensitive to electron beam. So the solubility of this resist changes when exposed with electrons. So let's look at what is the process and how we do it, and also how we increase the throughput of the system by doing some adaptation to the system. So there are primary requirements which we already saw earlier in optical as well. So the resolution, meaning here we need to have a very small feature, and the smallest is all we like, and the sensitivity of the resist is also very important, right. So you want minimum amount of electron, right, in order to create the chemical modification, right, in this case the solubility change. You don't want to spend too much energy. So that is the reason why the resist would be sensitive, right. So the chemical nature of the resist also plays an important role, right. That is because it is not just exposure, but then after exposure you are going to develop the resist and so on, and also the chain, right. So a long chain photoresist will have a lower resolution compared to a short chain resist, right. So these are all some typical resist, PMMA, HSQ, MAN. So these are all some standard resist that is used in electron beam writing, either positive or negative, and also their resolutions are also different in nature, right, based on the chemical composition. So unlike optical lithography, we have a special challenge here. The challenge is handling charging, right. What we are doing is we are shooting electrons, right. So when you take any dielectric substrate, let us say, right. So this is glass. So if I shoot electrons to this glass substrate, what is going to happen is there will be a charge cloud formed here, right. Why is that? Because electrons can't go anywhere, right, because the layer is insulating, right. But if you take a metal, right, so if this is a metal or a conducting substrate, right, this could be conducting substrate, then the electron would dissipate into the material, right, so that you will not have this cloud formed, right. So that is exactly the issue here, right. So if you take a dielectric material, then you start accumulating charge, and what is the problem with the charge accumulation? We have seen this multiple times in very small problems. So if you have a charge cloud which is negatively charged, and then I have electron beam which is also negatively charged, what will happen? This will deflect, right. The charge cloud here will deflect the beam. So this is something we use for electrostatic lens, right. But now you are creating this lens on the substrate itself, because you are unable to dissipate the charge accumulation here. So it will create focusing issue. You won't be able to focus it because of this beam deflection, right. So displacement and distortions are the issues that you see because of this charging. So what can we do, right? So that is the cartoon that is captured here, how your beam is getting deflected. So what to do to address this question, right, this challenge? So put some conducting layer, right. But that is can be easily said, but then we need to think about what do we mean by conducting layer here. So of course a conducting layer will take out whatever charge accumulation you have into this, right. but then this conducting layer should be thin enough, right, really thin enough that it will allow the electrons to pass through without losing the electrons there. Without loss of electrons you want to go through, right. It should be transparent to a large extent. It should not scatter the electrons, right. So you want it to be very thin, right. So you can use some sort of polymer, right, conducting polymer, or very thin layer of metal, right. It's very challenging to do it, but if you take an atomic layer of metal, or one atomic layer, two atomic layers, this should also do the job. But more often people use conducting polymers, right. So P dot PS is another example of one such conducting layer. There are many polymers one can use. So if you want to really have to address this charging issue, you can use this, but this strongly depends on the substrate, right. If you use a silicon substrate, you will not find this problem that much, but then once you go to substrates like sapphire substrates, or you have silicon dioxide as the top layer, right. It may be silicon substrate, but the top layer is silicon dioxide, you have this issue, or silicon nitride. So all these will have an issue of charging, right, while silicon itself may not have this issue. So the resolution, right, that is an important question in all lithography. So what is the resolution limited by, right. So when the electron gets into the resist, it normally gets scattered. That's primarily the starting process, right. It gets scattered, right, and once it achieves a certain energy, then it reacts with the polymer layer and induces chemical change, right. And the scattering depends on the energy of the electron, the substrate, and the pattern itself, right. So the scattering strongly depends on all of this, right. And how do we characterize this scattering? So this is a simulation of scattering. So you take a 30 kV beam and then a 100 kV beam. So if you look at it, 30 kV beam, the penetration depth is very small, right, and it will illuminate this this particular region, and then you will have a pattern defined here, okay. So when you increase the energy, you can see here how deep the electrons are going, right. So the electron penetration depth is very small, but when you look at high energy beams, obviously the beams penetrate deep into the material, and now you can see your exposure is very large, okay. So you have to think about whether my features will come out better with low energy or high energy. So in this case, lower energies are always better, right, compared to high energy. The real reason for that is not just the forward scattering, it's about the backward and secondary scattering as well. And that is the reason the bottom image shows you that the forward scattering, right, the forward scattering is pretty sharp here, but then it diverges quickly for a low energy, because the energy of the electron here is low, so it can scatter well. But then if you look at high energy, the forward beam is very very sharp, okay. So this is, from this we should not come to a conclusion that high energies beams are much sharper, and then we can define very fine features. But the real reason here is the exposure of the electron beam resist not only depend on forward scattering, but it primarily depends on the back scattering and the secondary scattering. See all these scatterings that we see here, this is all secondary scattering, and then the back scattering that you have. So once you achieve the necessary threshold, right, the contrast curve, you remember, right. So this is the energy of illumination, and this is your resist thickness, right. So it should go down, right. So if it reaches a certain energy beyond which you will expose, right. So if you take very high energy beam, you want to make sure that you only expose this part, right. But unfortunately, because of the secondary scattering, you are pushing this, right, further. So you will have all the adjacent regions also getting exposed. So when you are choosing your voltage, accelerating voltage, make sure that you know what kind of structure feature sizes that you are looking for and what is the resolution that you want. This is not only affecting your resolution but also proximity as well. We will see that in few minutes now. Right. So proximity depends on multiple things, right? As I mentioned, accelerating voltage, we just stopped there in the last slide, right? So accelerating voltage affects proximity, and proximity correction should be taken care in the design itself. It is very hard to control proximity correction or proximity error correction while you are writing, right? One way of doing that is by using, you know, double layer kind of resist that will help you in proximity correction. So what is proximity effect in electron beam litho? So the bottom left we have you know, two example. The structure has two different widths, right, and this is a negative resist. So that means this is where your electron beam is there, right? So here you expose and the exposed path stays, right? And if your energy is kept identical, right, and then if you increase the width, you will find a broader feature come out better compared to a narrow feature, right? So the reason for that is, you know, though you expose it, right, to keep it constant, what happens is you will have some fringe field, right, because of the scattering. So just to give you an idea, right, I am exposing it here and this will create a exposure volume, right, and then the next exposure is here and this is the area where I don't want to write, right, and then in this case also you write something like this, right. So now this portion is also written, right, you don't want to write but this portion is written, but when you use lower energy you will have very less amount of exposure here, so that your blanking part remains the same. So that is the reason why you know, your proximity effect can be controlled by your accelerating voltage as well. So one need to take care of what is the width here, right, and what is the voltage that you are going to do. Using this you should be able to handle proximity effect. In more sophisticated cases you can use a bilayer resist, right, a low sensitive and high sensitive resist that will, you know, reduce the acceleration, right, because the whole idea of changing this voltage is to reduce this, right. So another way of doing that is I can put this is layer 1 and layer 2, I can use this high acceleration voltage, but then this layer 1 is going to be very low sensitive material and that will primarily absorb most of the thing, and then your second layer which is highly sensitive but it will be exposed with lower energy here and so on, right. So this is how you can also tackle proximity effect, and this is what happens, right, in a real scenario, an isolated feature, right, and a dense feature. So if you look at this isolated feature, very nicely defined, right, but then if you look at a feature that has some structures on the side that is flanking it, you will find that you won't be able to get the right dimension that you want. The reason for that is the dose from these two will affect each other, and that will create undesirable critical dimension variation. So the best way to do that is to write large features and small features using different dose. In optical lithography you don't have this choice because you do a full illumination, right, but in this case you are writing. So that means I can change my energy in these locations, right, compared to so whatever I have inside, right. So in these locations I can use different energy, right, and then when it comes to the edges I can reduce my energy. So this is how you can do large area and small area features to address this proximity effect, right. So position dependent dose optimization is what you need in order to address proximity effect. So this has to be done at the design level itself, right. Before you write it, the design tool will help you in doing this position dependent dose optimization, right. And the next undesirable thing is the stitching error, right. What is stitching error? Because we are writing, we cannot write the whole wafer in one go, right, because the deflection region is fixed, right. So if the beam is coming and if this is a wafer, I only have a deflection range of delta x, right, and delta y in the other direction as well, right. And this is what it's called right field, the field within which we can write. And then if I want to write a large area, right, so this right field can be, let's say, 100 by 100 micrometer, right. If my area is 3-4 inch wafer, then it is impossible to write it with this field, right. So what we do is we write it field by field. We move the right field, right, by moving your wafer. But if our line is 1 millimeter, so what I should do is I should divide this line into this right field width and then stitch the line together, okay. So this is how you do it. So this is only a problem if your size of these features are larger than the right field that you have. If the features are within one right field, you will not face this stitching error, okay. If the right field, if your right field is smaller than your feature that you want to write, you will find this problem, right. So this is all about stitching, and you need to have this alignment error correction, right. So if you don't do it, this is what happens. So that is the SEM picture that you see. So this image looks reasonably continuous, right, without noticeable deflection, right. This is your right field boundary. So this is your right field boundary, right. So this is right field 1 and this is right field 2. So when you are moving from right field 1 to right field 2, you can see this is the structure is deliberately done to show this writing error. So at one point you can see here it is well aligned, but then you can see here, right. So there is a misalignment between the two right field. If you want a continuous line, unfortunately if you have right field misalignment, right field error, you will have this stitching error, okay. In the worst case you will have complete discontinuity. At least here you can see some continuity, right. But then if the lines are completely discontinuous, then the structure is useless, right, if you are doing electrical circuits. So we need to take care of the stitching error. So in recent systems, the stitching error is taken care by something called fixed beam moving stage, right. So instead of keeping the blanker, right, to write this particular right field and then move to the next location, right. So what is happening is here in this fixed beam moving stage, the beam deflection is minimal, right. So the beam is not deflected too much. In all practical sense, you can assume that the beam is fixed. There is no deflection to the beam. But what we do is we move the stage. We move the wafer left and right, right, up and down. You can do it, right, x and y. Basically, when I say up and down, it's not z, it's x and y. There is no change in the height. So if you do that, then there is no stitching at all, because the beam is fixed. You are continuously moving, right. And this continuous movement is taken care by laser interferometer stage, right. It's a high accuracy wafer interferometer stage that takes care of x movement and y movement, right. By doing this, we are able to write millimeter scale structures, right, with very high resolution without any stitching error at all, right. So this has allowed large area patterning without stitching error. That is very important. So there is no stitching error. Without stitching error, right. So you can write very large features, millimeter size features, because you are not deflecting. Your movement depends on the XY motor. Okay, so there is a XY motor that moves the stage in this. So you are only limited by that motor range, right, not by any of your electron beam deflection. Okay, and you have sophisticated interferometric setup to control the stage position. Okay. And overall the key metrics to look for any writing system is the resolution, right, and the resolution of any electron beam system is limited by the scattering of the electrons in the resist, right, and the electron resist resolution itself, the chemistry and so on, and the beam optics, right, the lens and so on, right. So direct writing of very narrow e-beam can be done, but this is done on resist, right. So if the material is electron beam sensitive, you can pattern it directly. If not, we do indirect patterning using resist, and you can also do it with templates. We will see that quickly because so far we just used only pencil beam, right, which is limited to the spot size we have. Is it possible to increase it? So you can do projection with templates so that you can increase the throughput of the system. So that is again very important factor, and also control the proximity, right. And one of the downside of all of this is this has to be in vacuum, and it is writing, so it takes longer, right. So it is longer, and also we have to do it in vacuum, which makes the system with slightly higher overhead compared to other systems, right. And this is how we can improve the throughput, right. Instead of using a pencil beam, you use a template, right. There is a shape that we use as a template, and then you can repeat that shape along the wafer, so that you can make a pattern. So for instance, if I want to write this pattern, very large pattern, so I will divide this into rectangles, right. So I can divide this into rectangles, and then I can write these kind of image, right. So what I need is this rectangle is done written in one go. This stepper, if you remember the stepper concept, right. So where you illuminate one area in one go, right, almost like a projection, but with using primitive structures, right, primitive shapes, and then we can do repeat and moving the stage, we should be able to write different patterns, right. So this will improve your throughput, but the downside here is, since you have to expand the beam, right, you will end up with lower energy on the wafer, right. So you have to increase your the beam current. So that means you need to increase the energy of your electron gun in order to match this. So this is how it is done. So on the left side you see the conventional way of writing, where you have the beam shaping, where you create the aperture, and then you have the lens system, and then you do the scanning, right. The scanning is done here, right. But on the right side, what you do is, instead of the aperture, the spot shaping, what you do is you do a mask. In this case, it's just a square, right, and the square is projected through the system, right. You will not see any change in the bottom half. The lens and the deflector remains the same. The only thing is, now the beam is already profiled. You have a square already, right. You are just projecting that square here. So since your beam is not a focused beam, you are going to expand the beam. Look at that, right. Your beam width is pretty large. So if the beam width is large, the current density would also be affected. So you should also take care of that energy in order to write these kind of patterns. And this is something that was demonstrated a while ago, right, to improve again throughput. for repetitive patterns, right. This will not work for arbitrary shapes. It will only work for repetitive pattern that uses scattering from the repetitive pattern you have, right, which is called scattering with angular limitation projection electron beam lithography. So we are looking at projection like system for electron beam lithography that uses scattering. So here you have the beam coming from your source, a profiled beam, and then you have the scattering objects, right, and these scattering objects is going to scatter the electron beam by using again the lens system, right. These lenses are electrostatic magnetic lenses that will capture the electrons and then project it onto the image, right. So this remained mostly a demonstrator, but this is one of the possibilities to do it. But recently people have come up with multi-beam writing, right. That is the most interesting part, where instead of using a single beam, you will use multiple beams, and these multiple beams will have individual deflectors, and these individual deflectors can write a multiple area. So what you are trying to address is you are going to increase your write field, right. So initially with a single beam, this was your write field delta x, let's say, but now n number of beams will increase my write field with the same quantity. So there are thousands of beams that one can use in order to do that, and that is called multi-beam writing, which is explored very seriously as an alternate writing process for next generation CMOS. So this is still in R&D phase. There is a startup that is working on this. We'll see how that evolves, but this is another interesting configuration that has evolved over the years. So with that we come to end of this lecture, where we elaborated on the resist process, and also how the energy is affecting your resolution through proximity and so on, and how to correct those. And also we saw alternate form of illumination by using shaped beams, right, that is to improve your throughput and so on. And also you can use multi-beam as well, which is again an evolving technology.